Okay, good morning, afternoon, or evening, everybody. Welcome to the Global Navigation Satellite System, or GNSS, Radio Occultation Science and Applications Earthdata webinar. This is your host, Jennifer Brennan. While everybody is logging in, we have two optional polls at the bottom left and middle portion of your page, and we do appreciate your feedback that we receive on these polls. I've got 2 p.m. Eastern Daylight Savings Time, so we are going to go ahead and get started. What I'd like to do first is go over a few logistics related to this webinar. To ensure the best audio experience, the conference has been placed in silent mode. However, if you have any issues or you have any questions, what I'd like for you to do is enter those into the Q&A pod, and you'll find that located on the lower right-hand corner of your screen. This works like a chat. Today's webinar will be recorded. The recording will be posted to our online Adobe Connect webinar catalog, as well as to our NASA Earthdata YouTube channel within a few days of completion. All registrants will receive an email with links to the recordings. As far as today's presentation files are concerned, those will be available by emailing our speaker directly, and I will include his contact information on the last slide at the end of today's webinar. Regarding timing, today's webinar is 1 hour long. 45 minutes are allocated to the presentation with an additional 15 minutes for the question and answer period. After our speaker has finished his presentation, we will then move to a final set of polling questions, and then from there we'll transition directly to the Q&A period. You will have an opportunity to ask your questions throughout all portions of the webinar, with the exception of during a short animation by using the Q&A pod. Again, this works like a chat. Questions will not be answered using the raising hand function. It has been disabled. And then just one final note, depending upon the volume of questions we receive today, we will extend the Q&A period an additional 10 minutes to 3:10 p.m. for those of you who may wish to stay on the line. What I'd like to do now is pull up today's agenda. So let me do that here for you. Okay, during the first few minutes, our speaker will provide an introduction to UCAR and describe the connection between the Cosmic Data Analysis and Archive Center, or CDAAC, and NASA's Crustal Dynamics Data Information System. From there, he will provide an introduction to GNSS radio occultation, highlight the current missions, and focus on several applications for this data. Finally, we will end with a quick look at the Cosmic 2 mission. With that, it is my pleasure to introduce today's speaker, Dr. Jan Weiss, who is a manager of the Cosmic Data Analysis and Archive Center, CDAAC, at the University Corporation for Atmospheric Research, or UCAR, in Boulder, Colorado. Dr. Weiss?
Okay, good afternoon from Boulder. Hello, everyone. Happy to be here to give this presentation on GNSS radio occultation science and applications. So we'll give an outline of the presentation. Jennifer reviewed this just now, so we'll go ahead and get started. And with a brief overview of the organization that I work in. So UCAR is the University Corporation for Atmospheric Research. This is a consortium of about 110 North American universities founded back in 1960. Primarily to operate the National Center for Atmospheric Research, which is here in Boulder, on behalf of the National Science Foundation and the university members. The organization has about 1,400 staff, 800 scientists and engineers. They have a broad range of expertise ranging from computational and observational facilities, big data sets, numerical modeling of the sun, atmosphere, and ocean system. You can see a picture on the right. They fly a couple of aircraft for test campaigns to do empirical measurements of atmospheric phenomena. The top picture is one of the facilities called the Mesa Lab. Sits right up against the foothills here in Boulder, and then there are various other facilities in the area. So my group is called the COSMIC program. COSMIC stands for Constellation Observing System for Meteorology, Ionosphere, and Climate. We're a little bit more than 25 staff, including scientists, engineers, programmers, software engineers, and IT and support staff. We have a broad range of expertise related to GNSS remote sensing. from ground and space-based observational instruments, in particular, of course, radio occultation. We'll be talking about that today. We also work on spacecraft integration and testing, data processing and operations, and then science applications related to weather, space weather, climate, and also a bit of geodesy. So we'll talk about some of this today. And so let's start with an overview of the GNSS radio occultation technique. Most people are familiar with GPS or GNSS for positioning and timing applications of receivers, on the ground, in a car, in an airplane, or in space. And primarily, what is used is a measurement of the range between the transmitter satellite that's up high in space at about 26,000 kilometers and the receiver. And if you take range measurements to enough satellites, then you can figure out both where you are and what the time is. So radio occultation is taking advantage of some signal. So this was originally developed for looking at planetary atmospheres, but if we focus on the Earth, it's taking advantage of these constellations of transmitter satellites that are up there. GPS was, of course, the first one for navigation. There's now a Russian system called GLONASS. There's a European system called Galileo, and also a Chinese system called BeiDou. And the technique is basically, let me get my pointer going here, looking at the bending of the radio waves transmitted from a GPS or GNSS satellite as it goes through, as they go through the atmosphere, and then receiving them on board a satellite, LEO satellite, in low Earth orbit. And so this is an illustration of that. And primarily, the fundamental quantity that is computed is known as the bending angle, and we'll talk about that a little bit later. And from that bending angle, which is sort of illustrated here, you can see the bending of the signals. Then you can get to a measure of the density of the atmosphere, which is refractivity, and from refractivity you can get to things like temperature. So there's an example on the right of a temperature profile for height versus temperature. The technique is also used to look at the ionosphere, so looking at total electron content and electron densities. We'll have a couple of examples of that coming up as well. So there's another picture, very similar, a little bit newer, that now has more than just GPS. We have some GNSS transmitters there, and then we have some radio occultation missions here. This is Cosmic 2 that I'm pointing at, and Cosmic 1 are those guys over there. And what I wanted to point out in particular on this slide is that you need a ground network, a GNSS receiver ground network. So that's illustrated over here on the left. And those GNSS receivers, you have geodetic quality, dual or triple frequency receivers, are used for a few different aspects that are very key to doing the radio occultation processing. One is the precise orbit determination for the GNSS transmitter satellites, so figuring out the orbit and clock parameters for those satellites with time very precisely. And the other part that's very important, that's illustrated here with this sort of bit transition example series there, is that you have to collect the raw navigation data message bits that are imposed on most of the GNSS signals. What we do is we collect those on the ground, make sure that we detect any errors and so on, and then those bits actually have to be applied to the measurements that are taken on board the LEO spacecraft. And because the tracking there is done in an open loop mode, and if you don't reconnect, or if you don't apply the bits, then you have these 180-degree phase shifts on your measurements, which would not be helpful. Okay, so CDDIS does also play an important role, and we greatly appreciate the fact that they are a reliable one-stop shop for terrestrial and space-based GNSS observation data, as well as products. So we use different aspects of this. So we use, as I just mentioned, the ground data. So many agencies around the world contribute GNSS ground receiver data, and we use them for GNSS clock determination in particular. We also get GNSS orbit and Earth orientation products, which are provided by the member agencies of the International GNSS Service, via CDDIS, and so it's a great service to have. We'll talk at the end. We've been deploying some receivers as well in support of Cosmic 2, and you know, sometime soon we hope to make some of those files available via CDDIS, so to also contribute to the archive there. So some characteristics of radio occultation data. I just highlighted a few things. I won't go through all of these. Just like GNSS navigation, the radio occultation technique from space using GNSS signals works globally. It doesn't matter where you are, whether it's over an ocean or over land. We get profiles of the ionosphere, the stratosphere, and the troposphere. The technique has been demonstrated to provide very high accuracy temperature profiles with an average accuracy of about 1/10 of a degree, so that's very good, and very high precision as well. Let's see, and the vertical resolution is interesting. It does work from you know, more or less it's close to the surface up to the tropopause and the stratosphere, so, and at those resolutions there. Some space weather items. The radio occultation sensors that are flying in space are used also to derive total electron content and electron density profiles. For TEC, the accuracy has been demonstrated to be better than 3 tech units, so that's nice. A couple of things that are really powerful in comparison to a lot of techniques out there that are used to sense the atmosphere is that there's really no calibration that's done with the RO instruments. So everything is tied to SI standards by way of the atomic clocks that are used on the GNSS transmitters. You don't really have to calibrate anything, and there's no instrumentation drift over time. As long as the instruments are functioning, you don't have to apply any particular corrections that change over time. And it's a relatively low power, low cost, and compact sensor. So those are just a few features. Scientific uses. So the big one is, of course, weather. So these days, all major global weather centers assimilate radio occultation profiles into their numerical weather prediction systems for their forecasts. So because it's a globally functioning technique, it's particularly useful over sparsely covered regions with other instruments, so the oceans and the southern hemisphere. And the technique has been demonstrated to improve numerical weather forecasts in various studies. I'll have a couple of examples later. And it's been very useful to look at tropical events and extreme weather events and interactions between weather systems around the world. Ionosphere and space weather. So you can use the space-based sensor data to derive global electron density and TEC distributions and look at those over time. The data are used for predictions of space weather events and the activity in the ionosphere, similar to weather forecasting. And you can look at all many kinds of interesting and unusual events that occur in the ionosphere, including scintillation, which are very high frequency changes in the ionosphere. So the RO technique has been, there's a nice phrase that's been coined in the community that it provides the world's most accurate, precise, and stable thermometer from space. And the technique now has existed and provided data sets for more than 20 years, starting with the GPS-MET mission back in the mid-90s. So you're getting to a point where you can really do climate and contribute to climate analyses and models and studies. So this is a high-level overview of the processing, and we won't go into great detail here, but it's top to bottom. So one of the first steps is precise orbit determination. So that applies to both the GNSS transmitters as well as the receiver in low Earth orbit. So we need to know where they are. We in particular care about their relative velocities and their relative positions. And once you have those positions precisely, then you compare, that's a geometric distance, which the signal would take if it were going through a vacuum. Now, of course, in reality, it goes through an atmosphere and is bent and slowed down. So we compare the measured signal relative to the geometric distance, and that's called the excess phase. and that's related to the Doppler of the signal, so that's why relative velocities are important. From that excess phase, you get to a quantity called the bending angle. I have an illustration of that on the next slide. And once you have the bending angle, then you can get to the density of the atmosphere or the refractivity, and from that you can go to other quantities like pressure and temperature. Okay, so this is a plot. This is showing a geometrical optics drawing of the geometry. So we have the GNSS transmitter providing a wavefront. That wavefront gets bent as it goes through the atmosphere, and then it's received over here at the LEO spacecraft. And this is the bending angle here. I'm skipping some of the details. But this approach is actually used in the operational processing up down to a tangent point altitude over the surface. That's the tangent point there of about 20 kilometers. And it doesn't work well below that, and then you get into a very complicated wave optics approach that's used. But in operational processing, both approaches are used. So refractivity, this is a model for refractivity, N, and it is a function of a few different things: pressure, temperature, water vapor, as well as the electron content. So we generally process dual frequency linear combinations of the GNSS measurements. That allows you to remove to first order the effect of the ionosphere, so that last term mostly drops out. And then you have a function of pressure, temperature, and water vapor. The operational weather models generally will take the bending angle, so one step before this, and then compute their own refractivity, and then run a filter that works out together with the background model what the and various constraints, what the different contributions are. And each weather center does this a bit differently, and it's a little bit there tends to be the more proprietary aspect of one of the proprietary aspects of what they do. Clock parameters. So this is unless you're doing time transfer, when you're working with GNSS, you tend to think of clocks as a nuisance parameter. So these are present in both the receiver as well as the transmitters. And we deal with them in radio occultation in a couple of different ways. So the one thing we can do is process undifferenced measurements, which means we have contributions from the receiver as well as the transmitter clocks in our measurements. So that means we have to introduce those parameters from external POD solutions for both the LEO and the GNSS transmitters. And that is typically what we do for post-processed applications, where we have a bit of time to get good, accurate, and vetted clock parameters for everything. That results in the lowest noise because we can just process the occulting link from the LEO satellite, so that's shown here, the one that's looking off to the limb of the Earth that's bent. For near real-time processing, we generally do a single difference approach, so that means we're now differencing the measurements on the occulting link here with a reference link for an up-high satellite. And that allows us to remove the common receiver clock parameter, but we still need to introduce the GNSS clocks from an external source. This does add noise to the solution because we're now looking at measurements from two different links, but the benefit is you don't have to worry about the receiver clock. In the old days, people also processed double difference combinations where a ground site was involved, two transmitters and two receivers. That removes all the clock parameters, but it adds different other things you don't want, like more noise and multipath. Okay, so that brings us to radio occultation missions. So we'll give an overview of some of these, and I'll start first by just introducing the CDAAC, the Cosmic Data Analysis and Archive Center, in a little bit more detail. So this CDAAC system is a processing and analysis system that runs in near real-time, post-processing, and reprocessing modes, and mostly focuses on GNSS RO data processing. And it involves many things, including dealing with data collection and data transfers and ingest quality control and those kinds of things. Then level 0 to level 3 processing, so all the way from the raw measurements to sort of gridded products. And many aspects related to this, for example, quality control and operations and product monitoring, delivering products to different customers, as well as data archiving. This system has been developed since the 90s and has been quasi-operational since the launch of Cosmic 1 in 2006, when these data really started to be used by the operational numerical weather community. We provide all the products and data freely and openly to the public via an FTP and a website. Some statistics on users are there at the bottom. And this is an overview diagram of the system. So this is a left-right diagram. So we have satellites in space. This is a Cosmic 1 satellite. And they downlink their measurement data via different paths, different downlink sites. And then they send them on to us. And so this is the processing center. We take those data in combination with other things, such as GNSS ground data, derived from or taken from real-time streams. There's a format called NTRIP, as well as file-based data sets. So CDDIS is an important contributor here. We use IGS, International GNSS Service Orbit, and clock products, and some other things from for example, the NOAA Global Forecast System, and various other things that are needed, metadata, and so on. And then we do the processing, and we come out with profiles of bending angles and refractivity, as well as the retrieved temperature, pressure, and water vapor sort of things, and provide them to different users. So for a mission like Cosmic 1, for example, that does get used operationally, we provide them on to NOAA, and there's a system called the Global Telecommunication System, where the data and the products are then shared with all the major weather agencies around the world. So the research community has access to the products and the data. We have also a close relationship with the Taiwan's Central Weather Bureau and their National Space Organization. Cosmic is a joint U.S.-Taiwan project. We provide products to the Air Force 557th Weather Wing. And of course, we archive all kinds of things, not just products, but raw data and everything in between. Okay. All right. So one of the very important missions in this field is Cosmic 1. So this was launched in 2006, and it's 6 spacecraft. There's a cover of a journal here that has pictures of them. So this was a demonstration mission. So these are, not very big satellites, but they've done a nice job. So the primary instrument is a JPL/Broadreach developed blackjack receiver for GPS only. There are 2 secondary instruments, an ionospheric photometer, as well as a tri-band beacon, but this one that did not get used very much. So I think we talked about the different products and observations that are available from the measurements that are taken on board the spacecraft. So as I mentioned, this was a demonstration mission. It was really meant for a 2-year lifetime originally, and luckily it's lasted much longer than that. And we're now down to 1 satellite still operating regularly, but that's been more than 11 years. So they're doing very well, these satellites. Okay, so when they were all functioning, this is a map showing the locations of the occultation profiles. So you can see, and those are the green dots, and you can see it covers the whole globe and works over the oceans and over areas of land where we don't have maybe a lot of ground-based observations. Behind the green dots are radio sonde locations. So these are launched from the ground and they, on a balloon, and they go up and take measurements of the atmosphere and record those and send those back to the ground. And so, occultation measurements are a nice complement to that because they do work globally. This is just a time series of the number of neutral atmosphere occultations that have been available from Cosmic 1 since the start of the mission. So when everything was working early on, the best of times, there were about 3,000 occultations per day. So of course that has decreased over time. And unfortunately in April we lost, there were 2 satellites that were working up until then, and we went down to 1, so now we're down to just 200 or 300 occultations per day. So we're definitely, you know, and we're not sure how much longer it's going to last. So. Okay. Now, there are many missions that have radio occultation sensors, not just Cosmic One. So this is a table of all the different missions that we process here at UCAR. So the first one was GPS MET. So that's here in about the middle. This is with anti-spoofing off. There were some experiments. So this was in 1995 and 96. And then there are counts here of the neutral atmosphere and the ionosphere occultations provided by each mission from current as of a couple days ago. So Cosmic One has provided more than 6.6 million occultations, so that is quite a lot. The European MetOp satellites are producing many as well, and you see a number of other missions here flying occultation receivers. So we're close to 12 million now in total, and 5 million for the atmospheric occultation or ionospheric occultation. All right, so science applications. So we'll just give a few examples of the impacts of RO data to some of these applications. So this time series here shows an analysis done by the European Center for Medium Weather Forecasting, ECMWF, and they started ingesting radio occultation data from Cosmic One not too long after launch. So this, and you can see where they started doing it. You see a real change there in the difference here, and this time series is showing the difference between radiosonde temperatures and their analysis at co-located regions. And once they started using simulating the RO data from Cosmic One, they saw a reduction in the bias seen in this time series, which is of course very nice. People have looked at the reduction in numerical weather prediction model forecast error at various times. So I'll just show a couple of examples here. So this is another study done at ECMWF back in 2011, so when Cosmic One was fully functional. And this it's a little bit hard to read, but there are various different observation types and sensors that they use in their global weather modeling. And so there's a lot there, as you can see. And then what they did is a data withholding study where they took out different contributions and looked at the impact and the degradation in forecast error to look at what each type of observation contributes. So we can see RO, I've highlighted it here, provided about a 10% improvement in their, or reduction in their forecast error, which is a very nice result. So it's in the top 5 or so of the different observing systems. And it's impressive because the amount of data was between 2 and 3% of all the data. So 2 to 3% of the data gave them about a 10% reduction in forecast error. Another study done at NCEP, that's NOAA's National Center for Environmental Prediction here in the States, looked at something similar back in for a period in 2010. And I'll just highlight here on the right side, so they also looked at this by impact per observation in forecast error reduction, so taking account of the data volumes from the different sensors. And you can see that RO comes in at number 3. So that, again, it's a technique that punches well above its weight in these systems. So this one, I'll just describe it a little bit, and then I'll ask Jennifer to switch to a movie. So of course, extreme weather events are predicting the occurrence or the genesis and the tracks of extreme weather events such as hurricanes and typhoons is of course very important to people living in many areas. And usually what happens when you go to do a simulation of RO data into a model is that there's a lot of quality control that goes on. And when you have a region where, say, a typhoon might be developing, the atmosphere will be fairly moist. And that may not agree very well with a background model or a prediction from an earlier model run. And that often will cause a lot of the RO data in that particular region to get kicked out in the QC up front and then not get used. Some colleagues of mine, Bill Kuo and Shiyue Chen, in the last few years have been looking at ways to use more RO data in regions where a hurricane or a typhoon might be developing, and to see if they can improve the forecast of that particular event. So this movie that we're going to show is a global numerical weather model prediction from 3 days out. And on the left side, we're going to see sort of a standard setup. See if my pointer works here. Yep. And on the right, we're going to use more radio occultation data. And what you'll see is, you'll see some action starting to develop on the right that you don't, and you don't see much of that on the left. So there, and you can clearly see by now that there's a typhoon developing. And just for geographic reference, this is the island of Taiwan there. And yeah, so there you go. Now you can clearly see there's a typhoon present where it wasn't in sort of the standard setup shown on the left. And this has since been published in a paper. I didn't put the reference in it, but we can provide that if needed. So, okay. Great. So I guess that we're showing it again. Yep. Thank you. Okay. A little bit on space weather. So there's a whole large body of work on applying radio occultation sensor measurements to the ionosphere and applications in space weather. This is just one example. So this is a researcher who was here, Shinan Yu, and some colleagues looked at combining measurements from space-based RO missions. In this case, you can see here Cosmic 1, CHAMP, GRACE, SAC-C, TerraSAR, and one of the MetOps, as well as some data from JSON 1 and 2, together with ground-based GNSS measurements to derive a 3D profile of the ionosphere, tomography through time. And they've done this analysis in this particular study from 2001 through 2012. This work has since been extended to bring it more to the current time. So you can see some examples here of a nice 3D picture of the ionosphere. And on the right is sort of the the space-based two-dimensional view that many people are familiar with, showing over time the transition of the sun around the Earth. Okay, so one thing that we've been very busy with here is in this group is the Cosmic 2 program, and so I'd like to just spend a few minutes describing that mission and some of the things we're looking forward to there. Okay, so Cosmic 2 is again a U.S. and Taiwan partnership. It's led by NOAA, the National Oceanic and Atmospheric Administration, and the U.S. Air Force on the U.S. side, and Taiwan's National Space Organization. Our group is involved in many aspects of this mission, including procuring and validating the instruments, the spacecraft hardware integration and testing, calibration and validation of the instruments once we get into space, the mission operations, including the Operational Data Processing Center, as well as the related science. So that will be very exciting once we get into space. So the Equatorial constellation for Cosmic 2 is currently planned for launch in Q2 of next year. It will be, again, 6 satellites, and they'll be in a low inclination 24-degree, 520-kilometer orbit. We expect about 6,000 or more, actually, occultations per day from this set of satellites when we're flying. So that's already double what we got with Cosmic 1. And we have pretty stringent latency requirements. So for ionospheric products, it's a 30-minute median requirement, and that means from collecting the data or the measurements on the spacecraft to the time that products are available on the ground. So, in particular on the data processing side, we actually don't have much time because a lot of your latency there is taken up by waiting for the downlink to happen. For neutral atmosphere, the latency requirement is a bit higher, and that is mainly because the numerical weather models don't run all that often. They kick them off every few hours, so the latency isn't quite as important for that. But this drives a lot of work on the downlink side. So there are 9 sites distributed around the world. Most of them are received, but 2 of them have uplink capability. The primary instrument is an update of the JPL Heritage Blackjack receiver, so it's called the TRIG for Tri-GNSS. For this mission, we'll be tracking GPS and GLONASS, so the Russian GNSS system. And that is one of the reasons why we will get many more occultations per satellite than we did with Cosmic 1. There are some secondary payloads. One is an in-situ instrument called the ion velocity meter. There's also a tri-band RF beacon also for studying the ionosphere. And there's a laser retroreflector, which will get used just a little bit for validating the microwave orbits. On the right, we have a picture of the Cosmic 2 satellite. This is a Surrey space technology bus. Weighs about 300 kilograms. It's got good star cameras and sun sensors, good attitude stabilization. And so we're looking forward to this. This will be very improved in terms of attitude control and just general quality, we think, relative to Cosmic 1. This is not a demonstration mission, but actually an operational mission. The first satellite was assembled at Surrey in the UK, and the rest were assembled and of course tested in Taiwan at NSPO. The mission is launching on a Falcon Heavy rocket provided by SpaceX, and it'll be launching at Kennedy Space Center. The satellites will be dropped off at an altitude of 800 kilometers, and then every few weeks one of them will transition down to the operational altitude of 520 to 550 kilometers. And that actually, from beginning to end, will take about 18 months. And here we have a picture of the rocket. Okay, so this is kind of what the satellites look like right now. They're in the clean room. So we have 1, 2, 3, 4, 5, 6. They're upside down there. In space, they'll be facing the other way. So this here is the in situ ion velocity meter. And then this is one of the GNSS antennas for receiving. And let me go back here. One thing that's a little bit unusual for both Cosmic 1 and Cosmic 2 is that the antennas that are used for POD are, first of all, you have two, and they're looking sideways. That's tilted by 75 degrees. Typically, you would put one antenna on the top facing in the zenith direction and use that for your POD tracking and analysis. And the reason for doing it this way is, and they did this in Cosmic 1 and it worked well, is that you can see through the ionosphere better with this kind of geometry. And so we'll do that again. And this time they're nicer antennas. They have choke rings to reduce multipath errors, whereas on Cosmic 1 they were just pretty simple patch antennas. So I mentioned this is a prediction of the occultation coverage from this set of Cosmic 2 satellites, and the low inclination orbit means that we get a lot of dense coverage between, it turns out, about 48 degrees, plus or minus 48 degrees latitude. And this was designed this way because that is where a lot of the extreme weather events like hurricanes and typhoons develop, and the radio occultation technique will help improve the forecasting of those events. So we're the Operational Data Processing Center, and we've done a lot of work to enhance that over the last few years to get ready for Cosmic 2. There's an enhanced data management system, so we're involved in coordinating the downlink scheduling and the telemetry data transfer between the different sites and the different centers that need the data. We've added GLONASS capability. Of course, I believe we'll have the first publicly available GLONASS data from space from Cosmic 2, so that's exciting. The low latency requirements that I already talked about have driven a lot of work not only on the downlink side, but also on the processing side to make sure we can meet those requirements. We've added capabilities for processing other sensors, so we're taking advantage of a modular processing framework with which CDAAC was designed and implemented, and now added, for example, the ion velocity meter processing into that framework. A lot of work has been done on the IT security side because it's an operational mission. There's a certification under a regime called FISMA you have to deal with. and we're now archiving everything in more than one place. So one in-house archive as well as one provided by NOAA. In order to ensure robustness and reliability of the processing, we're doing everything in two places. So geographic separation is a good way to get at that. So our primary processing center is in Cheyenne, Wyoming. That's about 100 miles north of here at the NCAR Wyoming Supercomputing Center. And here we'll be running two operational strings of all the processing. The idea being that it's much more likely for a single computer or some processing string to have a problem than the whole data center. So this data center is very nice. It's got redundant power suppliers and internet backbone connections, has redundant fiber connections here back down to Boulder, and it's also where we house the primary data archive. At the Mesa Lab facility here in Boulder, we'll have the backup data center. So this is where we have an additional staging/operation system, as well as our development system and another data archive. So. Okay, so now we'll turn our focus briefly back to the ground network. One fun part of getting ready for Cosmic 2 has been the upgrading and enhancement of a network that used to be called a bit grabber network. So this goes back a long time, but these were simple receivers that were collecting the raw navigation bits for other missions in the past. So we've been improving that now with commercial receivers that allow us to do this, and of course full GNSS tracking. And so here's a map of some of the sites. The blue dots are the ones that are operational right now. We have a few more in the works. And we also get some contributions from other agencies. So the data from our sites, we are already making available in real time where we can support it in terms of the comm situation at the different sites. And we're hoping to make the RANX files available in the next, in the near future, also via CDDIS. Just some pictures of the sites. So we're trying to do geodetic quality, triple frequency tracking, all in view GNSS kinds of setups, so that the data will be useful not just for our occultation processing, but for geodetic and atmospheric science in general. Okay, and then so I'll close with just a relatively high-level overview of the different pieces that are involved in the RO processing and retrieval techniques. And so I'll start here on the left. So there are a lot of inputs, and those are on the left. So we're going to start with GNSS orbits and clocks and EOPs. We need station coordinates, high-accuracy station port coordinates, as well as the observation data. So CDDIS plays a role in providing all of these. Again, a lot of different agencies are very nice and contribute these different data and products via that archive, so that it's easy for folks like us to use them. So we take those data and the products, and we do GNSS transmitter orbit and clock determination. So we're first estimating station positions, clocks, troposphere delays, phase biases, all kinds of stuff to work out what those transmitter orbits and clocks are. And then we feed those into the POD processing for the radio occultation satellites in low Earth orbit. So of course, if we go back here to the left, we need the actual data from the satellites, so the raw observations, the ranges and phases and so on, as well as ancillary data like the satellite attitude. And then we estimate what the satellite orbit and clock is. And then we take another data set which is provided by the spacecraft, so the occultation observations. So these are typically done at 50 to 100 hertz. And those are the limb viewing measurements taken from the satellite. And we combine them with some more ground data, so the navigation message bits, to figure out the excess phase. So again, the difference between the path traveled by the real signal through the atmosphere and what the geometric distance would be. Once you have that excess phase, then you can apply geometric and wave optics processing to come up with a bending angle profile. And from that, you can get to the atmospheric retrievals, so refractivity, and then pressure, temperature, humidity, and so on. And then those products are used by applications in the areas of weather, space weather, and climate. And all of this is done in near real time for some missions and in post-processing as well as reprocessing modes for many missions, as we showed earlier. So I just like to thank you for listening, and I'll just put up one more slide. We're definitely not the only people involved and contributing to this. There are many agencies that are contributing in one way or another to the existing missions as well as Cosmic 2. And we gratefully acknowledge everyone's contributions and the nice interactions we have around the world with our partners. So that closes my talk.
Okay, thank you, Dr. Weiss, and thank you, everybody. At this point, what we'll do is we'll move to a final set of polling questions. I will give these questions 2 to 3 minutes or so, and then from there we'll move directly to the Q&A period. All right, so do be sure to stay in the virtual meeting space and on the line, participate in the Q&A. All right, thanks, everybody. We'll give these just a couple minutes. Thank you. Okay, everybody, we'll give these questions just another minute or so, and then we'll move directly to the question and answer period. Okay, everybody, thank you. At this point, we're going to move to the question and answer period. Let me pull that up here. We did have some questions earlier on here. Okay, just really quickly here, we do have a number of, I think to date, we've got approximately 80 data discovery and data access webinars, all covering different disciplines, different data products or tools on our YouTube channel. That information is included here. And if you are interested in a copy of today's presentation, the PowerPoint slide deck, you'll need to email our speaker directly. I've included his information on this slide. And then a reminder, the recording will be posted within a couple of days of completion, and I will be sure to send those links to all registrants for this webinar. Now moving first to our question that was asked a bit ago. How many of the ground GNSS receivers are connected to hydrogen masers? I hope I'm pronouncing that correctly. And does this aid the GNSS POD and clock determination? Dr. Weiss?
Okay, so for our network, we don't have any masers. We have a few, I want to say about 3 to 4 rubidium or cesium type frequency references locally. Now, when you go and do the global processing for the GNSS orbit and clock determination, of course, a much larger network of receivers is available via, for example, CDDIS. And there are definitely sites there that are used that have hydrogen masers. And I think strictly you don't really need it, but it is good for to have a time scale that is close to UTC or GPS time. And so generally people do include at least one or two reference sites with hydrogen masers in their processing. And but in terms of RO processing, that actually doesn't really matter.
Okay, thank you. The next question includes a comment as well. On the Mars Global Surveyor for Radio Science Occultation Experiment, the stability of the ultra-stable oscillator determined the accuracy of the atmosphere and ionosphere soundings. What are the specifications for stability of the USOs on the LEO SC receiving GNSS signals?
So good question. So I don't have I don't have the Cosmic 2 spec in front of me, but that has been carefully thought about. So so there's a couple things here. So for example, for Cosmic 1, you will generally take single difference measurements. Say we're doing near real-time processing. And what we're going to do there, we're doing that, and we're going to add noise, but we're removing the effect of the receiver clock. And the reference link on Cosmic 2 and other missions that fly the Blackjack receiver or variation thereof are tracking both the occultation measurements and the reference link at, say, 50 hertz. So you can just directly difference those measurements. They're at this, they're relative to the, they're on the same receiver clock. And that's it. So that's nice. So for some other missions, for example, MetOp, they put an ultra-stable oscillator on the spacecraft. So there you don't have to track the reference link at the same rate you're tracking the occultation link. So you can take, say, 1 hertz data, and if you have a stable enough receiver clock, then you can interpolate those data and still do single difference processing. And for that's the approach we'll be taking for Cosmic 2 as well. And yeah, unfortunately, I don't have the receiver clock spec on me, but that has been carefully reviewed.
Okay, thank you. Now moving up to our next question. Extreme weather is on the rise in the polar regions, for example, off the coast of Alaska, Iceland, etc. What is the possibility of eventually including global coverage again?
Well, I hope that possibility is strong. So there is nominally a plan for a second set of Cosmic 2 satellites. That funding is a bit uncertain at the moment, but the idea is that those would be at a much higher inclination orbit, probably nominally 72 degrees, but it could even be higher than that based on some studies done recently. So that would be the idea, is that you then fill in those regions.
Okay, thank you. The next question is, I registered with TACC to download tech products, but I'm having issues accessing the data and products. Is there another website besides the tac.cwb.gov.tw, and so, or documentation that you can refer me to?
Yes, so you're welcome to contact me. So the other source, so TAC is the Taiwan Analysis Center for Cosmic, and so that's one place you can get these products. You can also get them from us. If you Google UCAR CDAAC, you'll find it easily, or you're welcome to contact me, and I'll point you to the right place.
Okay, so Sandra, I will follow up with the email information so that the two of you can be connected and see if you can't get to the bottom of the issue here. And then the next question is, let's see here. Oh, nope, it's more of a comment. Thank you for the talk. If there are any additional questions, what I'd like for you to do is enter those into the Q&A pod. At this point, I don't actually see additional questions, but we'll wait a few minutes here. Are there any additional questions? Just a couple of points while we're waiting to see if there are any additional questions. What we will do here is, with no further questions, we will log off from the audio component. Excuse me. All right, so the next question is, Orbit knowledge maps directly into errors of phase measurements. What are the orbit accuracy requirements of NRT GNSS and the LEO spacecraft orbit?
Okay, so that's a good question. Let's see. So the orbit accuracy. So let me think about Cosmic 2. That's where I have the specs. I believe for near real time, it's not real high on the position accuracy. I believe that's 25 centimeters 3D RMS, but the velocity is quite a bit tighter. And I'm actually going to look at this in real time because I do have it in a document here. Give me just 1 second so I get the numbers right.
Sure, no problem. And just a continuation here. What we'll do when there are no further questions, we'll log off from the audio component. However, I will leave the virtual meeting space open an additional 10 minutes or so. If anybody thinks of a question, you could jot that down into the Q&A pod.
Okay, so I already made a mistake. It's 15 centimeters 3D RMS for near real time, and the velocity is 0.15 millimeters per second 3D RMS. So that is really the main thing you care about. You want a reasonable knowledge of the orbit, but it's the position is not as important as it is, say, in altimetry applications. So one thing that in the RO that's kind of useful in this regard is that you typically, when you do your profile processing, you remove the first point. So any error that is a bias over the course of the occultation actually comes out, and so that helps you a lot in terms of the orbit position. So you don't care quite as much for that, but for velocity you do want a very accurate knowledge of the velocity.
Okay, thank you for that. The next question is there any reason why there are no planned stations at the southern region of South America?
Well, I would love to have some help on this, actually. That is an area we've been looking at. So yes, we would like to put a site, say, in southern Argentina or somewhere about there. But yes, because if you look at the coverage, sort of the South Atlantic and Southeast Pacific could use a little bit of improvement. And what we want, of course, is not just one receiver seeing a satellite over any given location, but hopefully about 3 at least, so that if a site here and there goes out sometimes, then you're robust against that. And it also allows you to do majority voting of the navigation bits.
Okay, thank you. Are there any additional questions for our speaker? And just a note, you can always feel free to email me as well if you have not made note of his contact information, and I will be happy to forward you along to Dr. Weiss. All right, I am taking a peek here to see if there are additional questions. It does not look like it. I'd like to thank all of you for joining us. And our next webinar will actually be held on, let's see here, August 23rd, and will focus on biogeochemical data at the NASA Oak Ridge National Laboratory, DAC. So stay tuned to our tinyurl.com Earthdata webinar for details. Okay, let's see, there is an additional question here. Can the receivers be installed on top of buildings, or do they have to be on the ground?
Buildings are fine. We just want sort of geodetic quality. But, yep. Just like the IGS sites, some are on the ground and some are on buildings. Mm-hmm.
Okay, wonderful. Thank you.
Mm-hmm. Yep.
Any additional questions? All right, it doesn't look like it. Thanks to everybody for your participation today, and thank you to our speaker, Dr. Weiss. And at this point in the webinar, what we will do is we will log off from the audio component, and again, I will leave the virtual meeting space open until 10 minutes from now, so let's see here, till 3:10. So if you think of something, feel free to note that within the Q&A. All right, thanks everybody. I hope to see you at an upcoming webinar.
Okay, thank you for listening.
All right, thank you. Bye-bye now.